Number 14. Very, all right, no, it's all right. Okay. First, this question, I like to give you a chance to practice mathematical induction. Yeah. Using mathematical induction to check if the statement is true or not. All right, yeah. So because for mathematical induction, let's try the base case first. When n equals 0, it's true, right? It's easy to check n equals 0. When n equals 1, can you check it? All right, yeah. It should not be very hard when n equals 1. You can check it if it is a positive integer or not. All right. After that, you need to make mathematical induction assumption, right? Yeah. But here, I like to tell you a very important identity. If you have that, then by the mathematical induction, you can get your conclusion. What is that critical identity? Let me show you this. Right. Yeah, here I just use the space for other questions. Okay, yeah. Continuation here. Yeah. All right. Look at this. Okay. All right. Multiply. This step, usually people do not realize to do this operation. Here, let me just do it. All right. Multiply all the terms out to n plus 2. Okay. And to n minus 2. Right? Yeah. Look at this equality. Okay. Yeah. Why it is important? Yeah. So let me write in this way. All right. Because for the mathematical induction, we can make induction assumption, right? Make your induction assumption using the way we use in our notes, induction assumption. In our notes, look at the notes. What is the way? Fibonacci formula in our notes. Go there, right? Induction assumption. All right, but you need to complete the last step, step 3. Here, the formula I give you, that's for your step 3. Look at this one. Step 3, we need to look at this expression, plus 2. All right. Yeah, I need a little more space. Yeah. All right, here. One over the structure from the above equality, we can write in this way. Okay. Yeah. Minus sorry, integral term first. Oh. Yeah, let me, yeah, I need to write this thing better. Yeah. All right. All right. This identity comes from this above identity. Okay. Yeah. I just move terms from left to right, right to left. Okay. Yeah. Now you need to examine this identity. All right. Closely examine this identity. All right. So this part, the structure, when K equals 2m plus 2, right? Yeah. K, yeah. And because here we consider phi, oh, sorry, phi, yeah. 2k plus 1 over phi to the 2k, all right? But this here, the k is not a 2. So here, k equals m plus 1, all right? M plus 1. All right, so that's the, the general form we are considering. Yeah. And then this one, this form, k equals n, right? This one, k equals n minus 1, right? Okay, yeah. All right. This square thing, can you verify? Remember the question mark before? Can you fix the question mark first? After that, these k equals n minus 1. Can you connect to the induction assumption? Can you connect to induction assumption? All right. After you connect, what conclusion you get from the left-hand side? Conclusion. From for step 3. Step 3 of mathematical induction. How about that? Okay, mathematical induction. That's the, main part of the work. If you understand the procedure of mathematical induction, then this part, you follow my hint. Here, I give you the hint. You follow this hint, you can make your conclusion correctly. How about that? But the bottom line is you need to be familiar with the mathematical induction, the basic concept, mathematical induction. And this is the one I want you to have a chance to practice mathematical induction. Okay, yeah. I do not ask you to write the proof. Here, it's a multiple choice. But your thinking relies on mathematical induction. Okay, all right, yeah. So any question? Yeah. Let me know. Any question? Okay. If no question, I will move to our regular lecture. All right? Yeah, because I don't want to waste time. All right? Yeah. But you're still, okay, chat message, let me check. when problem 3 and 5 ask which expression is larger, it's referring to function growth, correct? I assume so, but not certain. All right, yeah. Comac, all right, let me check that. Number 3, number 5. All right. Oh, yeah, number 3, number 5, faster growth function. Yeah, actually, what I ask you, you know, yeah, growth function. Yeah, so here, my intention, yeah, so yeah, let me say in this way. If you like to use growth function to see that, it's fine, yeah. But what I ask you for the long run, I just ask you the fact, all right? I just ask you the fact for the long run, if which expression is really larger. Long run, yeah, how do you understand the long run? I like you to understand when n goes to infinity, okay? When n goes to infinity, yeah. Because here, there is one thing many students could fall into the pit hole. So that is, some students just use the software to plug in some numbers. If you do in that way, it's hard to find the correct answer. The reason is these two expressions are really big. Can you plug in some huge number? It's hard, huge numbers. Yeah, because how can you make your experiment go to infinity, right? Yeah, that's hard to go to infinity. Yeah, one student told me, you know, plotting the graph of the function. If you look at the graph, still, you just see a portion of your graph, right? How can you see the behavior near the infinity? You cannot see the behavior near the infinity, right? You just see the portion on your computer screen that is too small, a very small portion you can see. So if you make your conclusion based on the graphs or your experiment results, then very likely you cannot get a correct answer. Yeah. The main reason is it's hard to go to infinity. All right. Yeah. But here to answer this question, B is a power function. A is an exponential function, right? Exponential function with A with the base. Yeah, we know A to the n with A greater than 1, right? Although you see so many 0, you know, 1 after decimal point, but still x greater than 1, right? When you compare exponential function with a power function with fixed number at the exponent, do we have any result for that, for it? Do we have any result for it? Yeah. In our notes, can you find the limit? Can you find, we computed this limit, D this time equals 1 million. How about that? Yeah, check our notes. This example, okay? Yeah, because this example, we really consider the limit. N goes to infinity limit, okay? Yeah. But when you do experiments, it's hard to make n goes to infinity. Okay, and that's the reason. You may not get right by experiments. Okay, yeah. So that's number 3. So I hope you get the point. Number 5. Yeah, number 5 is different. Yeah, number 5. I ask you to calculate the results. Calculate the results. Yeah. Not the growth function. Yeah, here the answer. Now using the growth function. Why? Yeah, do not use that concept. Why? The reason is, look at this, n takes one special value here. One special value. All right. For the growth function, we do not take special value. We consider n grows, n goes to infinity. When we look at the growth function, we look at the behavior when n goes to infinity. Here, it's not the situation. Here, n does not go to infinity. N takes one special value here. So that's not a growth function situation. Okay? Yeah. So you need to plug in and simplify your expression. So you get 2 numbers. A, after simplification, you get one answer. B, after simplification, you get another answer. Then you compare which one larger, which one smaller. Straightforward comparison. Okay? Straightforward comparison. That's number 5. Yeah. All right, Cormac, these 2 questions. Yeah. Yeah. Hope you get the point. Yeah. Yeah. Do not get confused. Yeah. All right. Other questions? So you can, use this chance, yeah, to ask. Yeah. All right. Yeah. Okay. Yeah. All right. Oh, yeah. I can post this file. Yeah. So I wrote a lot of handwriting on this PDF. Yeah. So when I save, if you need, I can post it. Okay. Yeah. So you can use it to study, this hint file. Okay. All right. All right. I will stop right here and start our new lecture. No. Yeah. Okay. All right. Okay. All right. Okay. Yeah. So we need to start a new. Yeah. Oh, yeah. I forgot to say one thing. I forgot to say one thing. Yeah. Why is that? Ooh, what's that? All right. I don't need that. One important thing, let me just dismiss this annoying thing first. Yeah, so that thing, I need to dismiss it. All right. Yeah. But there is another thing I like to let you know. Yeah, quite special. I just noticed that. So I need to let you know. All right, let me share my screen again. Do you know about the fall break? I remember in the syllabus time, I mentioned that a little bit. Syllabus, look at the October 19th, Wednesday, fall break begins at 11:30 p.m. That means our Thursday, October 20th, that is in the fall break period, because classes resume at 8 o'clock a.m. on October 24th. Look at that. That means our regular Thursday's class is in the fall break period, right? Yeah. That means we should not have our class in the fall break, right? Think about that. Okay. Yeah. So we will lose one class session due to the fall break. Yeah. So that's fine with me. Although I don't like to, lose any lecture session, yeah, but I have to follow the university schedule. Yeah. But for you, you just have more time to work on your homework assignment, because the homework assignment will due on Friday, right? Yeah, so you need more time to work. So on Thursday, we won't have our regular class. I will post announcement for, make sure everybody gets this message. Yeah. So Thursday, no class. Yeah. And yeah. So, okay. All right. Yeah, because based on this calendar. Yeah. All right. So let's start a new lecture. Yeah. Because similar to our spring break, in our spring break, the whole week, we do not have classes. But fall break shorter than spring break. Yeah, but still it is a break time, right? Yeah. All right. Part C of module 4, merge sort. We just learned insertion sort. It's pretty short, insertion sort, but it is quite useful. Okay. Yeah. Here, another useful sorting algorithm, merge sort. All right. Part C, C.1, introduction to merge sort. From the name, you can guess some very special. Are we going to wrap up the small portion of part B? Oh, good question. Yeah, comment. Yeah, you're right. I need to talk about that. We have a small portion, part B. That's the selection problem. Yeah, selection problem. Oh, yeah. Let me change the color. Yeah, good question. Yeah. Yeah, very good. You remind me. Yeah. All right. We have a last topic. It's a selection problem. In part B, yeah, I will talk about that. Okay, yeah. So I will talk about that at some time. Yeah, but here, let me do that merge sort first. Yeah. The selection problem, when I find some time, I have 15 minutes, I will first talk about the selection problem question. Then I give you the conclusion, but I do not go through the solution, how to solve it. Yeah, that's too long. And that will usually, very hard to understand. Okay, very hard to understand. But I just give you the conclusion. Yeah. All right. Yeah. So that's the selection problem. Yeah. All right. Yeah. I will. Yeah. So Comac. Yeah. So I will do that later. Yeah. Just try to remind me. So if I miss that part. Yeah. But I will do it before we end module 4. Now, module 4, we have part D, the quick sort. Yeah. Before I end module 4, I will talk about that selection problem. Okay. All right. Yeah. So let's continue our introduction, C.1, merge sort. Yeah. Problem number 13, merge two sorted arrays. Yeah. So we consider a small computing problem, merge two sorted arrays. Yeah. So the question is why we want to work on this question. What's the reason behind it? Yeah. So here, there is some reason. So let me describe the background for this question. Yeah. All right, first, the question description. Given two ordered arrays, how to merge them to get an ordered array. Yeah. So merge two ordered array, we want to get a larger ordered array. The whole array must be ordered. So we merged those two. Yeah. The question is, we want to find the best solution. Yeah. Best possible solution. Okay. Yeah. Not the best case, best possible overall solution. Okay. Yeah. All right. The motivation here, let me describe a very special situation where we need to use this result of this problem. Yeah. Okay. Yeah. So let's consider this question. How to sort a huge array. Still sorting, but the data is special. How special is the data? The data array is huge. How big it is? Here, let me describe how big it is. Yeah. Yeah. I use this line segment to represent this whole array, very big. Yeah. You can imagine this array is so big, it is stored on the hard drive, but the whole array cannot be loaded into the memory completely. We know our memory is much smaller than hard drive, right? Yeah. Look at the current typical memory size for a laptop. Yeah. Let me just use this 16 gigabytes. How about that? Yeah. My laptop, I only have 4 gigabytes. Okay. Very small. But it's good enough for my teaching, right? So here, I just assume 16 gigabytes. Yeah. Pretty big, right? But look at the, hard drive. Hard drive, some students may have the terabytes, right? So here I just assume 500 gigabytes. You can see much bigger than the memory size, right? Yeah. Here we assume our data can be stored on the hard drive, but it cannot be loaded completely into the memory. Okay, under that situation, can you sort that array? We know when we implement our algorithm, we need to load the data into the memory, usually, right? Yeah, because otherwise, how do you execute your program, your data on the hard disk? Yeah, all right. So here, to solve this problem, we need to find a special way to do it. Okay, yeah, so here, let me describe the way to do it. Yeah, we use divide and conquer way to do it. We want to break this huge array into smaller pieces. Yeah, all right, yeah, like this. Yeah, and each piece, we can load it into the main memory. Yeah, so we can do that. Yeah, each piece, we can load it into main memory, okay? In that way, we can sort each subarray piece by piece in ascending order like this, okay? Yeah, ascending order, yeah. But you can see the whole array is not sorted, right? Yeah, we conquer individual subarrays, but the whole array not sorted. In this situation, we need to merge two sorted arrays and to get the whole array sorted. Yeah. Here, yeah, because when we break the big array into smaller pieces, we can do parallel computing, right? We can send each subarray to one parallel processor, right? Yeah. So that means, you know, using this way, we have many use cases for this special divide and conquer way. Okay, yeah. But at the end, you need to merge two sorted arrays. That's the problem we are working here. Our problem number 13. Okay, yeah. So that's the background. Yeah. Motivation, yeah, for this question. Yeah. Next question, how to merge two sorted arrays. Yeah. So we need to solve this problem. It's not hard, yeah, but we want to go through the analysis work. Okay, all right. Given two arrays that are already sorted, how to get a new sorted array that contains all the elements. Yeah, so let's work on this new problem. Yeah. But when we work on it, we do not want to start from scratch. We want to use our old experience a little bit. Now, we want to borrow some our old experience. Yeah. In that way, yeah, so we can get a better understanding. Yeah. Here, we want to take advantage of the structured data. What's the structured data? Two subarrays are sorted. That's the structured data. Yeah. So we need to use that property. Yeah. Ordered property. Okay. Yeah. All right. Okay. All right. So now we have learned several sorting algorithms: selection sort, bubble sort, insertion sort, right? Yeah. In those sorting algorithms, some of them do not take advantage of the order information. Yeah. Look at the selection sort. Do we take advantage of order information in the selection sort? No, because no matter the order, what order is, ascending order, descending order, your selection sort uses the same number of comparisons. Yeah. Best case, worst case, the same number of comparisons. That means you do not take advantage of the order information. Okay. The bubble sort also, you do not take advantage of the order information. Yeah. Yeah. But here, I remember once before, one student sent me an email. Yeah, because on our textbook, there is a modified version of the bubble sort. Yeah. After every round scanning processing, it checks if there is any swap operation. If there is no swap operation, then it stops. The algorithm stops. Because no swap operation, that means it is already sorted. Okay? You do not need to do further scanning. Yeah, that's the modified bubble sort. It is described in our textbook. All right, yeah. So that student make this argument. Based on this algorithm, we take advantage of the order information. Yes, it's true. Yeah, it's true. Okay, yeah. In that modified version of bubble sort, we take advantage of the bubble sort, the order information. Yeah. All right. Okay. Yeah. Here, when we look at the insertion sort, do we take advantage of the order information in the insertion sort? Yeah. If we recall, if the data is in ascending order, here I'm talking about insertion sort. Okay. Yeah. If the data is already ordered, then the efficiency is big O of n. If it's not ordered, worst case, big O of n squared. That means the ordered information really helps us to improve the efficiency. We can do much better with ordered data. All right, that means this insertion sort takes advantage of the order information big time. Yeah, really big. All right, yeah. That means we can borrow the idea of this insertion sort and try to solve our current problem. Well, because they are related. The insertion sort and this merge operation, they are related. Yeah. Because mainly on the order information, how to take advantage of order information to improve the efficiency. Yeah. All right. Yeah, so after that, okay, yeah. Now let us work on the first, let's recall insertion step. Okay, from insertion step, we want to modify it a little bit to make it the merge step. How about that? Yeah. So we start with the insertion step. After that, yeah, so we need to make some modification. Then we try to find a solution of the merge operation. Okay, all right, so let's look at that insertion step. Yeah. All right, so let me still use the diagram. Insertion, we have a ordered array. This is ordered array, and a new key V, we want to insert it somewhere in this ordered array. Okay, so then we do comparisons, find right location, and then we make shift operations, then we complete the insertion. Yeah, remember that, right? Yeah. So that insertion step, yeah. Can we look at that insertion step in slightly different view here, right? Yeah. Can we change our view a little bit here? Yeah. So here we treat this one key element. Can we treat it as one element array? It is a special array, right? It is an array, but it just has one element in this array. Okay, one element array, and it is sorted, right? Think about that. One element array, it must be sorted. All right. Now, can we treat that insertion step as the merge step, merging two sorted arrays, right? but just the smaller array is a special one element array. Yeah. So here you can see the difference between our insertion operation and the merge operation is the merge operation is just a general version of insertion operation, right? Yeah, a general version. Yeah. Make that one element array to multi-element array extension. How about that? Okay, make that kind of extension. That's the relationship between these two operations. Okay, yeah. All right. Yeah, so sorted. Or we can say our insertion operation is just a special case of the merge operation. Okay, so you can see the relationship. Yeah. All right. So the new interpretation, two solid arrays are combined to get a new solid array. Yeah. But just one is a special, has a special structure. Okay. Yeah, we can make it a little more general. Yeah. So that's the, this new view, merge two sorted arrays for a new sorted array. That's the merge operation. Look at that. So insertion operation is a special case of the merge operation. Okay, yeah, all right. Since we have solved the insertion operation, so we try to use the similar way to solve the merge operation. Okay, yeah, all right. So let us apply the new merge view. Okay, all right. The new merge view for the insertion operation, we merge two subarrays with data sizes k and 1. Okay, yeah, k and 1. Yeah, it's not balanced, right? Yeah, because the difference is big. Yeah, and the data distribution is not balanced. Remember the data distribution thing, I talked about balancing principle before. Yeah. Look at that, the balancing principle. When we study the binary search, we observe some balancing principle. If we make data distribution as even as possible, we will get better performance. That's the balancing principle. Yeah. But here, if we use the insertion way, the data distribution is not balanced. Yeah. So that means its worst case won't be good. Yeah. Yeah. It may have a good best case efficiency, but because your data distribution is unbalanced, so you usually, most of the time, you won't get a good worst case efficiency. Right? Yeah. So here, for our new sorting algorithm, we want to have a good worst case efficiency. Yeah. Insertion sort, the worst case efficiency is bad, big O of n squared. We are not satisfied with this one, so it's not good, right? It's a bottleneck, too slow. Yeah. So when we consider a new sorting algorithm, we want to greatly improve this worst case. Big O of n squared, worst case. Okay, yeah. So how to improve? In our data distribution, we want to make balanced data distribution. That's the main arrangement we want to do here. Yeah. All right. Yeah. So yeah. So poor worst case. Yeah. Improve by balancing principle. Try to make two subarray of equal size. Yeah. As equal as possible. Yeah. We may have one difference. Yeah. Because when you have all the number of elements, even you try to break it evenly. Yeah. We end up with two subarrays. One has one more element than the other. That is fine. Yeah, only one small difference. Yeah, so we just take it. Yeah, All right, then let's look at C.2, the merge operation. We want to merge two subarrays with almost equal data size, almost equal, okay? Yeah. All right. How to achieve balanced subarrays? Divide and conquer. When we split the original array, we try to split it in the midpoint. How about that? Not median, midpoint, okay? Yeah, yeah. Do not get confused with the median, all right? Yeah, we split it at approximately at the midpoint, yeah. Whenever we merge two subarrays, we make them of equal size. Yeah. So that's for our data splitting. Yeah. When we do data splitting, we try our best to distribute the data evenly. Yeah. Let's look at this line segment. That is the original array. Yeah. All the data items are arranged in this line segment, okay? All right. Let us make our first split, yeah, in the middle, yeah, almost even, okay? Yeah. So let's say what we use this midpoint, yeah, approximate midpoint. So we have two subarrays. After that, the second round, split evenly in the middle of two subarrays like this. Third round, another midpoint split, okay, in this way and so on. All right. Yeah, but we have to stop splitting somewhere. Yeah, because when you have one element subarray, you cannot split, right? Yeah. At the end, you have all the subarrays are one element array. So you have to stop. Okay, yeah. After that, we can merge two adjacent sorted arrays. Yeah? Because for one element array, you do not need to do any comparison. One element array, we treat it as sorted, right? So after that, we merge two adjacent sorted arrays. Yeah, so first round merge like this. After that, second round merge, two adjacent larger subarrays. How about that? Every round, we merge two adjacent subarrays in this way, okay? All right, yeah. Then another round, and finally, the last round, we merge two final subarrays, and we get one whole array sorted. How about that, this procedure? That's the idea. That's the divide and conquer. All right, we split, even split. When we conquer, yeah, you know, for the one element case, we do not need to do anything. Then we can merge two adjacent sorted arrays, round by round, and finally we get a whole array sorted. That is the procedure. All right. Yeah. This diagram gives us that procedure, the idea. Okay. Next, we just need to implement it. Okay. Yeah. We just, you know, make the details for this idea. Yeah. Fill in all the details. Yeah. And we hope, because we do even split for our data, so we can expect to have pretty good worst case efficiency. We can avoid poor worst case efficiency. Okay, that's our goal here. All right. Yeah, so here you can see, to make the whole procedure work, we only need to solve that merge step. One typical merge step, merging two adjacent sorted arrays. Then we're done. Okay. If we can solve that general merge operation problem, then we solve the whole problem. Okay. Yeah. Next, let us work on the general merge step. Yeah. These two subarrays, we assume they are sorted. Yeah. All right. Then when we do comparisons, when we start, let us compare the two leftmost elements, A0 and B0. A0 is the smallest in left subarray, and B0 is the smallest in right subarray, right? After one comparison, we get a minimum of those two elements, A0, B0. We get a minimum, all right? The minimum, can we say that minimum 0, that this element is the minimum of all data counting A subarray, B subarray, all data, the global minimum. Can we say that? This main 0, we can say this main 0 is the global minimum. Okay? If it is global minimum, it must be the first element in the sorted array, right? Yeah, minimum. Its position is the first one in the sorted array. Okay? With that, yeah, so we have the minimum 0 and the maximum 0. Yeah, two cases. Yeah. All right. Then we try to place the elements in place. Yeah. So this sequence of empty locations, we try to place the elements in place in these empty locations. Yeah. Because after the first comparison, we can get a global minimum. That global minimum should be in the first location of the sorted array, right? So we put that element in place. That element, one comparison, we can put one element in place. How about that? Okay, just one comparison. We know we get the global minimum and we can put it in place. All right, yeah. But the remaining one, that max 0, we don't know its location. Okay, max 0, we don't know its location. Here, there are two possibilities. Max 0 could be A0 and it could be B0. Yeah. Here we consider case 1, max 0 is B0. Yeah. Then our next comparison should be, we compare B0 and A1. This time, the smaller one, we denote it as min 1. Min 1, all right? This min 1 should be in the second location of the sorted array, right? Yeah. Second location in the sorted array. So we can place it in place. Yeah. So you can see after our second comparison, we put another element in place and so on. We can do this kind of comparisons on, and at the end, yeah. So the second to last element, yeah, after one comparison, we can put it in place. But last one, we don't need to do comparison. Yeah. Because for the last one, there is only one position left for the last element. So we just put it in place. Okay, yeah. Here you can see for this merge procedure, how many comparisons do we need? Yeah, it's not hard to figure out, right? How many comparisons do we need to put all elements in place? Here we need to consider best case, worst case. Best case and worst case, all right? Yeah. So let's look at the number of comparisons for the worst case. Yeah. For the worst case, you need to do comparisons from beginning to second to last. Okay, yeah, that's the worst case. Second to last, you need one comparison. That's the worst case. All right. So the answer is 2k minus 1. 2k minus 1. We have total 2k elements, but for the last one, no comparison. Last one, no comparison. Yeah. Other than the last one, for each element, we need a one comparison. That's the worst case. Okay, so that's why we need 2k minus 1 comparison. Okay, yeah. All right. Yeah. So here we consider the general merge step. How general it is. Left subarray, we have m elements. Left subarray, we have n elements. They have different number of elements. That's the general case. Yeah. Because our thinking is the same, right? Yeah. The same as our previous slide. So we just modify slightly. We can get this general merge step easily. Yeah. Why not just get this general result? Maybe later it is useful. Yeah. So let's get the similar answer. Merge two sorted arrays of sizes m and n, respectively. The worst case solution is m minus n minus 1. Yeah. The reason is the same because for the last element, no comparison. Other than that, each of the, first m plus n minus 1 element, we need one comparison. Okay, 1 for 1. So we have total m plus n minus 1 comparison. Okay, yeah. So that's the worst case, the general case. Yeah. All right. Similarly, let's work on the, so the, general case, the best case. Yeah. Best case. Here, let's look at the best case. Yeah. The strategy. How do we get the best case? Yeah. For the best case, we want to find the case with the minimum number of comparisons, right? Minimum number of comparisons. That's the best case. Yeah. How to get a minimum number of comparisons? Okay, yeah. The strategy, try to exhaust one of the two arrays as early as possible. Look at that. If we exhaust one of the two subarrays, that means for the remaining elements, we do not need to do any comparison, right? Because you already exhaust one of the subarrays. You just put the remaining elements in place directly. Look at that view. Okay, yeah. Try to exhaust one of the two arrays as early as possible. Okay, all right. Yeah. How to do that? The question. How to implement the strategy? Yeah. We have two subarrays. One, right? We assume one shorter, the other longer. Yeah, we have two options. We can exhaust one of the two subarrays. Can we exhaust the shorter array? Yeah, because when we exhaust shorter array, that means we only need to do fewer comparisons. Yeah, shorter array, right? Yeah, okay, yeah. So the best case efficiency, we only do those comparisons to exhaust a shorter array. How to exhaust? We use the first element of the longer array to beat all the elements in the shorter array. Look at that scenario, okay? We assume we can use the minimum element in the longer array to beat all the elements in the shorter
subarray. When that happens, we only need to do the minimum of these two array sizes, M and N, because you exhaust the shorter array with this many comparisons. Okay, yeah. So for the general case, we need this many comparisons. Okay, yeah. So here we complete the, the general case. Yeah. Finally, C.3, efficiency analysis for the merge sort. Yes. Here, let me just describe the idea quickly. Yeah. So, yeah, because we just understand in the, visual way, in some visual way. Yeah. We derive recurrence relation. Yeah. Yeah. Let us estimate the worst case efficiency because we want to get a good worst case efficiency. The reason we choose this sorting algorithm, we want to have better worst case efficiency. Yeah. All right, so let's look at this given array. Yeah. All right, we assume we need a T of n number of comparisons to sort the whole array using the merge sort. Then we split it, even split, right? Yeah, to approximately even number of elements. So the two array sizes, half size, approximately half size, n over 2. So for the left subarray, we need T of n over 2 number of comparisons. Right subarray also this many comparisons. All right. Then when we merge, yeah, we just did it, the merge for the worst case. N minus 1, right? Yeah. Actually, based on our conclusion, N minus 1, but here that minus 1 is not important. We just use N. Okay, yeah, we just use N here. So the equation becomes this equation. Two base cases, the recurrence relation T of N equals 2 times T of N over 2 plus that merge step N. Okay, so now we need to solve this recurrence relation. Okay, yeah. Here we consider simpler case. When n is power of 2, in that way n over 2, we always get integers. Yeah, so that's the easiest situation we want to have. So we simplify the recurrence relation like this. Yeah, all right. Then we transform. Yeah, we use some little trick here. We do division method. What special division we do? We divide it by both sides by power of 2, 2 to the kth power. Okay, yeah. Why we do that special division? Because that division method would reveal the structure of this new equation, the structure. So what's the structure? Look at this left-hand side structure, right-hand structure. Are they similar? These two fractional expressions are similar, right? Yeah. So we explore the similarity of these two structures. Okay, similar structures. Yeah. So we define a new function. That new function g of k equals this t of 2 to the kth over 2 to the kth. Yeah. Because after this substitution, we will get a easier new recurrence relation. This simple. Look at that, how simple it is, right? This recurrence relation can be solved easily. Yeah, look at that. Okay, yeah. Here, how to keep track of these numbers. K minus 1 plus 1 equals k. K minus 2 plus 2 equals k. So we have this invariant property. Size plus that constant equals the fixed number k. Yeah. This property helps us to keep track of all these equations. At the end, when size equals 1, the constant part should be k minus 1 because their sum must be that k number. Okay, so we keep track of all these numbers. Yeah, and because g of 1 equals 1/2, so we have k minus 1/2. Okay, all right. Then when we go back to our original expression, yeah, so we have t of 2 to the k equals this expression. But we need to go back to the, go back to the n representation, right? Yeah, yeah, because n equals 2 to the k. We need to go back to n expression. Yeah. So k equals log of n. So our t of n approximately equal to n log n. Look at that, n log n. Okay, so this gives us some, good estimate. Okay, so this is good estimate. All right, we use the special case n equals power of 2 to get this expression. That means we only know this relationship works for n equals power of 2. Now, the question is, if n is not power of 2, does it work? Do we still have this n log n relationship? Yeah, we will answer that question next time. All right? Yeah, so let us stop right here. We will complete the last step of this method, yeah, for the general n. Okay? All right, so let's stop right here.